Hello, today we're going to talk about derivatives of exponential functions. The derivative of e to the x is e to the x itself. Remember, it's an exponential function because the variable is in the exponent. If the base isn't e, it's just a little bit more complicated. The derivative of a base that's not e to the x, a to the x, is itself a to the x times the natural log of the base. So for example, if your function was y equals 4 to the x, then the derivative would be 4 to the x times the natural log of 4. Now, it may be a little hard to just accept that the derivative of e to the x is itself. So let's try to use the limit of the difference quotient, the definition of a derivative, the limit as h approaches 0 of f of x plus h would be e to the x plus h, minus f of x, which is e to the x over h. Now remember, what we try to do is see if we can simplify this so that we can cancel the h out of the denominator and plug 0 in for h. Well, looking at this one, when we have two exponents being added, we can think of that as the base to each of those exponents being multiplied together. So we could factor an e to the x out of that, which would leave us e to the h minus 1 in the numerator, but it doesn't let us cancel out the h. And in fact, there's no way you can manipulate this algebraically to make that h go away out of the denominator. So our option would be to try numerical methods. The only problem with numerical methods is they can only give you answers for the value of the derivative at a point instead of the function for the derivative at any point. However, if we take a look at it on the calculator, I have put the difference quotient for the exponential function e to the x near 0 into the calculator. And then I'm going to go to the tables, but I'm going to go to the table settings first. And I'm going to start my table at 0. No, actually, I'm going to start it at, I'm actually not going to start it anywhere. I'm going to change the independent variable to ask, because then it's going to ask me what x values I want to plug in. So remember, the thing I have in the calculator is the difference quotient. I'm supposed to be taking the limit as h approaches 0, where I used x for h. And I was using this to find the value of the derivative of e to the x near x equals 0. So when I go to my table settings, I'm going to put in negative 0.1, negative 0.01, negative 0.001, negative 0.0001. 0 is not going to work. Then I'm going to put positive 0.0001, positive 0.001, positive 0.01, and positive 0.1. So if you look at the values, as that h got closer and closer to 0, just to the left of it we had 0.99995, and just to the right of it we had 1.0001. So it looks like the limit as h approached 0 was 1. Now that was for e to the 0 power, which is 1. So I'm going to go in and I'm going to change my function now, and instead of doing it near e equals 0, I'm going to do it near e equals 1. So I'm going to go back to my table. Notice it's still got all the same values, so I'm going to, but this is for h, not for x. So this is still as h approaches 0. So as h approaches 0, here we have 2.781 and 2.7184. And if you put your cursor over on those, 2.7181459, 2.718417748 e to the first power is 2.71828 blah 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 blah. So if we go in here to our settings again, and again I'm going to put it on ask. Well, I guess it didn't do that, but I'm going to just try some lower values of x, or ones that are closer to 0. So I'm going to go up, and I'm just going to put negative 0.000001 and positive 0.000001. Now, notice that what shows in the list is identical. Down here we have 2.7182804, 2.7182832. So this value is getting closer and closer to e to the first power. And since we were taking the derivative of e to the x as x was near 1, that's what shows us that the derivative is e to the x numerically. Now we're going to use this to do some problems. And the most common mistakes that I see students make on these problems is they've already learned about the power rule, and they get the power rule and the exponential rules confused with each other. Remember, a power function has x in the base. An exponential function has x in the exponent. So looking at our function f of x here, the first piece of this, the x is in the base. The second piece of this, the x is in the exponent. Pi, even though it's a symbol, it's still just a constant value. So you treat it like any other constant. So for the power part of this function, x to the pi squared, we bring the exponent down in front as a constant multiple. We keep the base of x, and we reduce the exponent by 1. Now, since pi squared isn't a number that we can just subtract 1 from and have a number, we just write pi squared minus 1. Now, because this function consists of a sum of two other functions, now we're just going to add the derivative of the other part. Well, this one is exponential. Its base is pi squared, which again is just a constant, and its variable is x. So the derivative of an exponential function is itself, so I just copy pi squared to the x, but then I have to multiply it by the natural log of its base, pi squared. Now, one other little thing that you can remember when you have logarithms of something with a power, you can bring the power down in front. So another way to write this would be pi squared times x to the pi squared minus 1 plus 2 pi squared to the x, or you can use the exponential rules to make that pi to the 2x times the natural log of pi. In this example, we have 5 times 5 to the t plus 6 times 6 to the t. The 5 and the 6 in the beginnings are just constant multiples. The 5 to the t and the 6 to the t are exponential functions. So the constant multiple comes along for the ride. 5 to the t is its own derivative as long as you multiply it by the natural log of its base, 5. Then the 6 is a constant multiple, so I carry that along. And then the derivative of 6 to the t is itself times the natural log of 6. There's nothing I can factor out of that to simplify it, so that's all I can do with that one. Now, if you wanted to, you could combine these together to make this 5 to the t plus 1 times the natural log of 5 and 6 to the t plus 1 times the natural log of 6. Wouldn't make a whole lot of difference. In this example, again, we have two separate pieces separated by addition or subtraction, so we can do the derivatives separately. 3z, z is just a power function with a power of 1. So the derivative of 3z is just the 3. The minus 2 is a constant multiple, so it's going to get carried along. And then 4 to the z is an exponential function, So its derivative is itself times the natural log of its base.